Welcome back. Now in this particular module, we have a total of 3 concepts that we are going to discuss in detail. Who are they? The first one is atomic size, the second one is atomic mass, and the third one that we are going to discuss is called as valency. Let's tackle them one by one. Let's begin. Now understand, if I talk about a pencil, the central axis of the pencil is made up of graphite. Graphite is nothing but a form of carbon. So I can say that the central axis, the lead of the pencil, is made up of carbon atoms. In a similar manner, if I continue, I can say that the smallest atom ever possible is the hydrogen atom. Now over here, a hydrogen atom has a single proton into the center. The nucleus does not have any neutrons, and we have an electron which is present in the orbit in the shell. And what am I supposed to do? I am supposed to compare the atomic size for hydrogen and carbon. Effectively, what am I trying to do? I am trying to classify a definition which is called as atomic size and what factors affect the atomic size of a particular atom, of a particular element. Let's begin. Okay, so as far as the size of a particular atom is considered, how are we exactly supposed to measure the size? The field ion microscope image over here is going to show iridium atoms, and to be honest, every spot on this particular image is an atom. So you all must understand how small iridium atoms are, how small any kind of atoms are. So to understand them, to measure them is an incredibly difficult process, but we are going to help you out do exactly the same. Okay, so as far as atomic size is considered, the size of an atom is determined by its radius, which is called as the atomic radius. What is the atomic radius, you'll ask me? The atomic radius of an isolated atom, an atom which is present all by itself, is the distance between the center of the nucleus of the atom and the outermost orbit. I repeat, atomic radius is the distance between the nucleus of the atom and the outermost shell. If you want a diagrammatic representation for the same, there we have it. Who do we have here? We have the sodium atom, given by the symbol Na, having an atomic number of 11 and having a mass number of 23. To measure the atomic radius of this particular atom, I must start from the center of the atom, which is the nucleus of the atom. And till where should I go? I should go to the outermost shell. So that distance that you see over here is nothing but the atomic radius or the atomic size. Remember, sodium has a mass number of 23. So an atomic number of 11 and a mass number of 23 is how a sodium atom is ultimately described. Okay, so do we have next here? Let's have a look. The atomic size depends on a number of factors. What are the factors on which atomic size depends? Let's have a look. The atomic size depends upon the number of shells. The atomic radius and the number of shells are directly proportional, which means more the number of shells, more is the atomic radius. Let's have proof for the same. Who do we have here? We have an atom of lithium. It has an atomic number of 3, configuration 2,1, 2 shells. Then we have sodium, atomic number 11, configuration 281, 3 shells. Then we have potassium, having an atomic number of 19, configuration 2881, 3 shells. And in a similar manner, rubidium is going to have 4 shells. So lithium, 2 shells, sodium, 3 shells, potassium, 4 shells, rubidium, 5 shells. You all can see clearly onto the screen. It's very obvious. As the number of shells increases, atomic radius is also going to increase, which means the number of shells and the atomic radius for a particular atom are considered to be directly proportional. Who do we have next? Next we have something which is called as nuclear charge. What is nuclear charge, you'll ask? Nuclear charge is the charge on the nucleus. Who are the subatomic particles present within the nucleus which can actually give it nuclear charge? Yes, absolutely. Positively charged particles called as protons. And what does the number of protons depend upon? It depends upon the atomic number. Now think about this. More the atomic number, more are the number of protons. More is the number of positive charge on the nucleus, more is the nuclear charge. Nuclear charge and atomic radius are considered to be inversely proportional. Why? Because when the nuclear charge increases, the force of attraction between the nucleus and the outermost shell is going to increase. More the force of attraction, more the electrons are drawn towards the nucleus, and because the electrons are drawn towards the nucleus, the atom is going to shrink, as a result of which more the nuclear charge, more the force of attraction, more is the attraction of electrons towards the nucleus, the atom is going to shrink and the atomic radius is going to decrease. So summarizing it for you, the number of shells and the atomic radius are directly proportional. More the number of shells, more is the atomic radius. However, the nuclear charge and atomic radius are inversely proportional. More the nuclear charge, lesser is the atomic radius. Atomic radius over here, understand, is expressed in nanometers. What is 1 nanometer, would you ask me? It is 1 upon 10 raised to 9th of a meter. That's how small a single nanometer is. In that particular case, if you take a single meter, divide it into 10 raised to 9 parts, a single part is 1 nanometer. Now, as far as atomic mass is considered, let's have a look. The number p plus n, which is called as the mass number, in the atomic nucleus is called as the atomic mass number. Protons and neutrons together are called as nucleons. Why so? Because protons and neutrons, both of them are present in the nucleus. Both of them are residents of the nucleus. Therefore, both of them are called as nucleons. The relative mass of an atom was therefore put forth. You need to understand the atom. You need to compare it to another atom so that you can get the mass of a particular atom. Therefore, we have relative mass of an atom. The relative mass of hydrogen was taken as 1. So, I will tell you all what is exactly happening over here. I need to understand the mass of various elements. I need to understand the mass of various atoms. I need a standard of comparison. Who is the standard of comparison? Hydrogen. So, when you take hydrogen, the mass of a single atom of hydrogen is going to be 1, and this single atom of hydrogen is going to be your standard of comparison for all other elements. Since you are comparing all the other atoms in relation to hydrogen, we get relative atomic mass. So, say suppose we have hydrogen, nitrogen, oxygen, sodium, aluminium, phosphorus, potassium. Let's select an element over here. Let us take nitrogen. I want the mass of a single atom of nitrogen. The mass of a single atom of nitrogen is 14 times heavier as compared to a single atom of hydrogen. So, if I take 14 atoms of hydrogen and I place them in one arm of the bean balance and I place a single atom of nitrogen onto the other arm of the bean balance, both of them will be balanced perfectly. So, I can say that the mass of a nitrogen atom is 14 times heavier as compared to the mass of a single hydrogen atom. So, there we have it. We have 14 atoms of hydrogen to the right, 1 atom of nitrogen to the left, and they are perfectly balanced. But there is a problem over here. Initially, hydrogen was taken as the standard of comparison. Then the standard of comparison was changed to carbon, which is a relatively more abundant element, which is a relatively more easily available element. But the problem is, carbon as a whole, the atom as a whole, is having a mass of approximately 12. Now, 12 cannot be taken as standard of comparison. So, what do? I take the entire atom of carbon, divide it into a total of 12 parts. In that particular case, if the entire atom has a mass of 12 and I divide it into a total of 12 parts, one part of that is going to have a mass of 1, which is exactly what we are looking for. So, we are going to take a single part over here as 1/12 the mass of a carbon atom, so that we can define atomic mass in relation to it. Have a look. Beam balance over here. Who do we have to the left? Sodium. Sodium has a mass of 23. How many 1/12 the mass of a carbon atom would I require on this particular part? Yes, I'll be requiring 23 of those parts, 23 of 1/12 the mass of a carbon atom parts, so that I can get the two beam balances perfectly balanced. There we have it, the relative atomic masses of some elements over here. Hence, instead of all of this, we took the unified mass. It has now been expected as the unit of atomic mass. It is called as a Dalton, and what is the figure of that? Its symbol is U, and it has a value of 1.66 into 10 raised to minus 27 kg. This is the currently accepted atomic mass system unit. Finally, we have chemical symbols of elements that we are going to discuss as the next concept. Now, Dalton used certain signs to represent elements. The kinds of signs that he has used are there onto the screen for you. We have hydrogen, carbon, oxygen, phosphorus, sulfur, iron, copper, lead, silver, gold, platinum and mercury. Do you think we use these symbols anymore? Absolutely not. So Dalton's symbols are only of historical importance. They are not used anymore. So we have a better way. Who are we going to take into consideration? The current method of choosing the chemical symbols is based on the method which is invented by the scientist Berzelius. Today we use the symbols which have been determined by IUPAC, that is IUPAC, International Union of Pure and Applied Chemistry. Let's have a look what they are exactly doing. According to this method, the symbol of an element is either the first letter which is placed in capital or the second letter over here with the particular name. Of the two letters, say suppose if you take a total of two letters, the first one has to be capital and the second one is going to be small. Let's have examples for the same. Okay, hydrogen has a symbol of H, first letter to be placed in capital. Oxygen has a symbol of O, first letter to be placed in capital. But now the problem is there are various elements which are going to start with H, there are various elements which are going to start with O. So in this particular case, rather than taking just the first letter, you take the first and another letter which is present in that particular spelling. Have a look. So we have carbon, copper, chlorine, calcium, cadmium. We need the symbols for all of them. But the problem is all of them start with the letter C. So for carbon, what do? We take the first letter as C itself. So the symbol of carbon is going to be C. But for calcium, it is going to be C followed by A. C in capital, A in small. The symbol of cadmium is obviously going to be Cd. And in a similar manner, the symbol of chlorine is going to be Cl. Finally, there are certain elements where we take the Latin name. So for copper, the Latin name is cuprum. And from there, we are going to get the symbol over here as Cu. Okay, moving on. I am going to give you symbols of some elements with their English names. Have a look. Name of the element is iodine. Symbol will be I. Uranium will be U. Cobalt, Co. Nickel, Ni. Barium, Ba. Bromine, Br. Krypton, Kr. Xenon, Xe. Manganese, Mn. Zinc, Zn. In a similar manner, what could we do is, we could take the English name. If the English name is not working out, you go to the Latin name and therefore you derive the symbol. Sodium is called as natrium, therefore Na. Potassium is kalium, so K. Iron is ferrum, therefore Fe. Copper is cuprum, as we just discussed, Cu. Silver is argentum, becomes Ag. Gold is aurum, Au. Mercury is hydrargyrum, Hg. Lead is plumbum, Pb. Tin is stannum, Sn, and finally we have tungsten, which is coming from its German name, Wolfram, which is called as W.